Phosphorus pentachloride. Phosphorus pentachloride is the chemical compound with the formula PCl5. It is one of the most important phosphorus chlorides, others being PCl3 and POCl3. PCl5 finds use as a chlorinating reagent. It is a colorless, water-sensitive and moisture-sensitive solid, although commercial samples can be yellowish and contaminated with hydrogen chloride. Structure. The structures for the phosphorus chlorides are invariably consistent with V-separ theory. The structure of PCl5 depends on its environment. Gaseous and molten PCl5, a neutral molecule with trigonal bipyramidal geometry and D3 symmetry. Hypervalent nature of this species as well as of PCl6, see below, can be explained with the inclusion of non-bonding molecular orbitals, molecular orbital theory, or resonance valence bond theory. This trigonal bipyramidal structure persists in nonpolar solvents, such as CS2 and CCl4. In the solid state, PCl5 is an ionic compound, formulated PCl plus 4 PCl6. In solutions of polar solvents, PCl5 undergoes self-ionization. Dilute solutions dissociate according to the following equilibrium. PCl5 equals PCl plus 4 plus Cl. At higher concentrations, a second equilibrium becomes more prevalent. 2-PCl5 equals PCl plus 4 plus PCl6. The cation PCl plus 4 and the anion PCl6 are tetrahedral and octahedral, respectively. At one time, PCl5 in solution was thought to form a dimeric structure, P2Cl10, but this suggestion is not supported by Raman spectroscopic measurements. Related pentachlorides. SCl5 and SbCl5 also adopt trigonal bipyramidal structures. The relevant bond distances are 211 pm as Clec, 221 pm as Clax, 227 pm Sb Clec, and 233 3 pm Sb Clax. At low temperatures, SbCl5 converts to the dimer, deoctahedral Sb2Cl10, structurally related to niobium pentachloride. Preparation. PCl5 is prepared by the chlorination of PCl3. This reaction is used to produce around 10,000 tons of PCl5 per year as of 2000. PCl3 plus Cl2 equals PCl5 DH equals 124 kJ/mol. PCl5 exists in equilibrium with PCl3 and chlorine, and at 180 deg C the degree of dissociation is about 40%. Because of this equilibrium, samples of PCl5 often contain chlorine, which imparts a greenish coloration. Reactions. Hydrolysis. In its most characteristic reaction, PCl5 reacts upon contact with water to release hydrogen chloride and give phosphorus oxides. The first hydrolysis product is phosphorus oxychloride. PCl5 plus H2O POCl3 plus 2HCl in hot water. Hydrolysis proceeds completely to orthophosphoric acid. PCl5 plus 4H2OH3 POFR plus 5HCl. Lewis acidity. Phosphorus pentachloride is a Lewis acid. This property underpins many of its characteristic reactions: autoionization, chlorinations, hydrolysis. A well-studied adduct is PCl5 pyridine. Chlorination of organic compounds. In synthetic chemistry, two classes of chlorination are usually of interest: oxidative chlorinations and substitutive chlorinations. Oxidative chlorinations entail the transfer of Cl2 from the reagent to the substrate. Substitutive chlorinations entail replacement of O or OH groups with chloride. PCl5 can be used for both processes. Upon treatment with PCl5, carboxylic acids convert to the corresponding acyl chloride. The following mechanism has been proposed. It also converts alcohols to alkyl chlorides. Thionyl chloride is more commonly used in the laboratory because the resultant sulfur dioxide is more easily separated from the organic products than is POCl3. PCl5 reacts with a tertiary of amides, such as dimethylformamide DMF, to give dimethylchloromethylneammonium chloride, which is called the Vilsmeier reagent, CH3-2N equals CCl-HCl. More typically, a related salt is generated from the reaction of DMF and POCl3. Such reagents are useful in the preparation of derivatives of benzaldehyde by formylation and for the conversion of COH groups into CCl groups. Is especially renowned for the conversion of C equals O groups to CCl2 groups. For example, benzophenone and phosphorus pentachloride react to give the diphenyl dichloromethane C6H520CO plus PCl5 C6H520CCl2 plus POCl3. The electrophilic character of PCl5 is highlighted by its reaction with styrene to give, after hydrolysis, phosphonic acid derivatives. Comparison with related reagents. Both PCl3 and PCl5 convert R3COH groups to the chloride R3CCl. The pentachloride is, however, a source of chlorine in many reactions. It chlorinates allylic and benzylic CH bonds. PCl5 bears a greater resemblance to S-OTWO-Cl2, also a source of Cl2. For oxidative chlorinations on the laboratory scale, sulfuryl chloride is often preferred over PCl5's. Gaseous S-OTWO byproduct is readily separated. Chlorination of inorganic compounds. As for the reactions with organic compounds, the use of PCl5 has been superseded by S-OTWO-Cl2. The reaction of phosphorus pentoxide and PCl5 produces POCl3, which is an unstable compound. 6-PCl5 plus for oten 10-POCl3 PCl5 chlorinates nitrogen dioxide to form unstable nitrile chloride. PCl5 plus 2N-OTWO PCl3 plus 2N-OTWO Cl. 2N-OTWO Cl2N-OTWO plus Cl2 PCl5 is a precursor for lithium hexafluorophosphate, LiPF6. Lithium hexafluorophosphate is a commonly employed salt in electrolytes in lithium-ion batteries. LiPF6 is produced by the reaction of PCl5 with lithium fluoride, with lithium chloride as a side product. PCl5 plus 6 LiF LiPF6 plus 5 LiCl. Safety. PCl5 is a dangerous substance as it reacts violently with water. It is also corrosive when in contact with skin and can be fatal when inhaled. History. Phosphorus pentachloride was first prepared in 1808 by the English chemist Humphrey Davy. Davy's analysis of phosphorus pentachloride was inaccurate. The first accurate analysis was provided in 1816 by the French chemist Pierre-Louis Dulong.